right, hi guys. This is the last part of chapter 17. We're just finishing up practices 16 and 17. And then we're going to be technically done with chemical equilibrium. So what we'll be moving into next after today is doing some mastering on chapter 17, doing some just generalized equilibrium review because we need to finish up the equilibrium unit before we move into our last unit, which is going to be on thermochemistry and electrochemistry. Wow, I'm really sorry that took me so long to remember. But okay, so last couple things you guys need to know about chapter 17 slash just this equilibrium concept in general is we've got amphoterism and solubility. So amphoteric oxides and hydroxides are soluble in strong acids or bases because they can act as either acids or bases. That's what amphoteric means, right? Like when do you know that when that's going to happen? Usually these are like the most common examples is when you have an oxide or a hydroxide of aluminum, chromium, zinc, or tin. Okay, so those are kind of like the four to look out for because they're the most common, all right? So more importantly, what we're going to be looking at in this practice is will a precipitate form. So you guys did some predictions of whether or not a precipitate was going to form because you knew your solubility rules. But now we're bringing KSP into those solubility rules. So to decide if a precipitate is going to form, you're going to calculate the reaction quotient, Q, which you should remember, I believe, from chapter 15, and compare it to the solubility product constant, KSP, which again, Appendix D, or it'll be provided to you in some way. And then we're going to do something similar with the comparison of the reaction quotient to the equilibrium constant. Now we know if K or Q equals K, the system is at equilibrium and the solution is saturated. But if Q is less than the KSP, more of the solid can dissolve. So no precipitate is going to actually form at that time. It just means that the equilibrium system isn't established yet. So you can throw some more of that solid in there and it will dissolve. It's not going to precipitate out into anything else. And then if Q is greater than KSP, then a precipitate is going to form because you are above your equilibrium point at that point. So obviously a precipitate can form because it's not going to be able to dissolve anymore. Okay. So let's look at an example of how you would have to precipitate or predict that in a particular circumstance. So it says, does a precipitate form when 0.10 liters of 8.0 times 10 to the negative third molar lead nitrate is added to 0.40 liters of 5.0 times 10 to the negative third molar sodium sulfate? Okay. So again, I just throw all that stuff up there, but we'll kind of break it down piece to piece. So what's happening here is the problem just wants us to know whether a precipitate forms. Okay, so whenever you see that, does a precipitate form, you should think to yourself, they're either going to ask me about solubility rules or they're going to ask me to actually calculate a KSP or a Q and evaluate the KSP as in comparison to the Q. So you're going to actually be looking for a KSP value because sodium nitrate is soluble. You guys should know that because nitrates are soluble, right? And like all sodium salts, right? But lead sulfate has a KSP because it's one of those ones that is not necessarily a strong electrolyte. It doesn't follow the solubility rules per se, but it will have a little bit of solubility there too. It's going to precipitate if the lead and the sulfate concentrations are high enough for Q to exceed KSP. So another thing to note is we are specifically adding 0.10 liters of lead nitrate and 0.40 liters of sodium sulfate. So overall, your volume in this system is going to be different. You're gonna need to put that volume together and create the value 0.5. Okay, so what they want you to do is come up with your new molar concentration based on your new volume. So if I take this first value of 0.10 liters and I change it into my number of moles that I actually have by using this value, the molarity, that means I'm just going to do a simple multiplication problem and I get this many moles of lead, okay? But now this many moles of lead are dissolved in 0.5 liters, right? So when I divide that, I get my new concentration of lead ions is 1.6 times 10 to the negative third, okay? You're going to do something similar for the sodium sulfate. You're going to take that 0.4 value, multiply it by the number of moles per liter in the molar concentration, and you get 2.0 times 10 to the negative third moles. So now you have the actual constant. Oh, I'm sorry. And then you're going to divide it by the 0.5, right? Because you need the new molar concentration, which now is 4.0 times 10 to the negative third. So these right here are your new concentrations of your free ions in the solution. So we're trying to predict whether lead sulfate would form, okay? And we're going to do that by just making a very simple like equilibrium expression where I need to multiply these values by each other. And so we say 1.6 times 10 to the negative third, which we calculated here, and 4.0 times 10 to the negative third, which we calculated here. And you get 6.4 times 10 to the negative 6, okay? So taking a look at the good old-fashioned Appendix D, where we would predict that from this combination, right? It's a double displacement, obviously. So we've got lead combining with the sulfate and sodium combining with the nitrate. So we know that sodium's going to remain aqueous. We know nitrate's going to remain aqueous. So we really want to know, is this precipitate of lead sulfate going to be forming? So we have to look at the KSP, which again is in Appendix D, and we talked about it before. So we're going to compare this value to this value. Oops, whoa, my mouse is all over the place. So is the precipitate going to form? Yes. Why is it going to form? Just form. It's not going to perform. It's because the Q is greater than that KSP value. So there's going to be a precipitate. Okay? So go ahead and finish practice 16. Give the video a pause at this point, and then come back and check. All right. So if you did this correctly, you should have found that 16.1, yes. 16.2, yes. And again, it's because the Q is going to be greater than the KSP, okay? All right, so we're on to the last practice that you guys have to do for practice 17. And this is a little complex. You can read through this chart. It is really informative and it's really good procedure and it's really good background information. It's just letting you know that you can use differences in solubilities of salts to separate ions in a mixture. So it's kind of just like a physical separation technique to get different ions, right? This has been used for qualitative analysis of the presence of ions in a solution. So it is pretty cool. It's an interesting technique, but we're not going to do too much with that, okay? So a solution contains 1.0 times 10 to the negative 2 molar silver and 2.0 times 10 to the negative 2 molar lead. When chlorine ion is added, both silver chloride and lead chloride can precipitate, okay? So they're asking what concentration of chlorine is necessary to begin the precipitation of each salt. First, that's what we're going to talk about, and then which salt precipitates first. So we're just going to be looking at these as separate entities with their separate KSPs, and we'll be doing some comparing as well. Okay, so again, we're looking at what concentration of chlorine is necessary to begin the precipitation from a solution containing lead and silver ions. And then we also need to predict which chloride or which metal chloride will begin to precipitate first, okay? We're given the KSP. Using these in the metal ion concentrations, we can calculate what Cl concentration is necessary to precipitate each salt. Okay, so what do we mean by that? Well, let's start here with the first KSP of silver chloride. Okay, if I set my KSP expression up, I've got KSP equals, and then I would say concentration of silver, concentration of chloride, and they already plugs in the value for the concentration of silver. It's right here, right? It already told you what concentration of silver you have. So if I'm going to set that equal to 1.8 times 10 to the negative 10th, then I can solve for the concentration of chloride that would be necessary to begin the precipitation, right? Because this is your equilibrium concentration. As soon as you exceed that concentration, you're going to start getting a precipitate. Okay, so they're going to do the same thing with lead, with the second one, lead chloride. So once again, KSP equals concentration of lead, concentration of chlorine. Why is this 2 here? Because of the formula. Some of you guys were missing that in the do now today, so make sure you're like revising that knowledge, okay? So we're still setting it equal to the KSP, which once again was given to us in this last slide, okay? It should be on your paper. You got it. So we're going to put the concentration of the lead. We're going to see chlorine squared equals, and then the KSP. So you're doing the same thing. You're just mathematically solving for Cl. This time you are going to have to take a square root to get to the concentration of chlorine. But the concentration ultimately is 2.9 times 10 to the negative second. So for the second ion to form, or precipitate to form, it has to exceed, the concentration of chlorine has to exceed 2.9 times 10 to the negative second. Okay. So to answer the second problem, which is which salt precipitates first, well, obviously it's going to be the one in the lower concentration, right? You're going to compare the chlorine concentration required to precipitate each salt. You can see from what we calculated that when chlorine is added, the silver chloride precipitates first because it requires a smaller concentration. So as you're pouring in, potentially what they're talking about, if you can see from this last slide, is that what they're talking about is maybe pouring in hydrochloric acid, which is a strong acid. So you are getting like purely like chlorine ions when you pour that in. So as you're pouring that in, first silver chloride is going to precipitate because of that smaller concentration value that we calculated. And second, lead chloride is going to form or precipitate, right? So if you want to just keep silver ions present, or like if you just want one precipitate, it needs to be between 1.8 times 10 to the negative 8th, which is the value we recalculated here, and this value, because once you reach this value or concentration of chlorine ions, you are going to see a precipitate of lead chlorate as well, or chloride, I'm sorry. Okay, so finish up practice 7, pause, then check. Okay, I realized I just said practice 7. I meant 17, obviously, right? Should have gotten C. Okay, that's just a conceptual check on understanding what's happening. And then for 17.2, if you did all the necessary math, you should have found that copper hydroxide precipitates first. Okay, and that is the rest of equilibrium. We are finished with equilibrium at this point. So like I said, be prepared to move into some mastering on equilibrium. Be prepared to move into some or I'm sorry, mastering on chapter 17, and then just some general review on all of equilibrium. So that's going to be 15, 16, 17. Okay. Also, this was my spring break. I didn't really get to see you guys afterwards. So the highlight of my spring break was just doing my baby's first birthday party. It was a lot of fun. Okay. I'll talk to you guys later. Bye.